All right, so I'm going to start out with the first worksheet, our series parallel example that we have here. And what I'll do is let's try to make this a little bit smaller so we can work with it here. And what you'll notice on here, that's where I can see it, is that we've got now this circuit where we've got the positive, right, and then the negative side of the battery here. And so we know that the current flow in this case is going up here, running into that first resistor. And then the current goes down this way and it goes down in a parallel form, hence the term series parallel. Then all that current, right, comes back here, same thing, right? And then ultimately ends up going back to the unit. So whatever the total current is out of this, what the total current is back. So the first thing I want to focus on, that's probably the most important, is let's take a look at our parallel side. So we're going to focus on this R2 and this R3. Okay. We can also plug in here the values to make it a little bit easier. So we'll put over here 12 volts, right? And then our total current is established as 3 amps coming out. So we know we got 3 amps coming back, right? And then we got R2 is 4 ohms, okay? And then R3 is 4 ohms, okay? But we don't know what R1 is, okay? So in order to figure this out, the first thing that we probably would want to do is figure out our equivalent resistance of this whole circuit, which is going to be a little bit tough because we don't have that R1 value. But let's start with R2 and R3. Once again, this would be our RT value, right, is equal to, and I'm solving for what? Let me make sure that I point out what I'm solving here. I'm going to be looking at R2 and then R3. So what is the equivalent resistance of these two values where it comes down on these two sides, okay? So let's go back there. And I'm going to put in here for that value. We've got 1 over 4, right? Plus 1 over 4, which is going to be 1 over RT is equal to 0.25 plus 0.25, which means we've got 1 over RT equal to 0.50. And then we're going to need the reciprocal of that. So RT becomes this, and then we're going to divide the 1 by 0.5, right? So let's see what we get there. That should be fairly easy. And it's going to give us 2. So we know that the total resistance going through R2 and R3 through that branch, and that should make sense, right? Because we, again, following our rules, we know that it's always half. So now what we can do is we can rewrite this example. So I'm gonna basically draw it as best I can here, right here. And then we've got this R1 that we don't know, right? And then, which is, sorry, I should have put the, and now rather than have the parallel circuits, we have an equivalent resistance here of what, 2 ohms. That's what we just solved for. And then coming back, right? Just like this. So now we have these circuits in series. We know that this is 12 volts, and we know that the current, right, is 3 amps. So now we can write out Ohm's law, right? Volts is equal to current times resistance. And so our voltage value would be 12. And then our current value is 3. And then our resistance is going to be R1 plus 2, right? We got 2, which is actually R2. So R1 plus R2 in series, right? We add them together. And so 12 is now equal 3 times R1, which is going to be 3R1 plus 3 times 2 is 6. we would subtract the 6. We end up with 6 is equal to 3R1. Divide both sides by 3, and R1 is equal to 2. To what? 2 ohms. Okay. So now, if we go back to our first picture here, we could put in 2 ohms now for R1 is what we've solved this for. Okay. And if we're curious, like, does that make sense? Well, we've got through the series we've got a total resistance equivalence of this unit, remember, was 2 ohms. So that's less than the parallel branches. That makes sense. And our amperage now going through here, we could actually start to calculate these. Because we know at this point, I'm going to show you here, at this point right here, right, we've got what, 12 volts. And then there's going to be a voltage drop, right, between these 2 points. Remember how we did that before? So if I bring these together, what would my voltage drop be there? Well, we know the amperage and the resistance here. So 12 here, right, 2 times 3 is going to be what? 6 volts, right? 2 times 3 using Ohm's law. So we've used up 6 volts. So we know on this side, at this point, and at this point, we've got 6 volts, okay? 6 volts, and then from there, the other question might be, well, okay, through the series circuit, we know if we got 3 going through this resistor, we got 3 amps coming out. Well, we have 3 amps going out the outside. We don't know that 3 amps is going down that branch, except that we've got an equal a number of these. But we could figure that out, right? Because 6 divided by 4 would give us the amperage that's going through this leg, right? And 6 divided by 4 is 1.5 amps, right? And then we've got down here 1.5 amps, right? So now, if we add that all together, right, we got 3 amps going through. We know we got 3 amps coming out of the series, right? And then it would split into this parallel. But if we add both of these branches, right, that we've just solved for, right, this one plus this one, we get 3. That's what would come through each one of these legs, 3 through here. And when it comes back, 1.5 equals 3 amps. We know that our answer is sound in this case. All right, so let's take a look at, I think it's worksheet 1, question 3. I'm going to bring that in right now. And you can see here, I'm going to kind of make it small because it's just easier to work with so we can talk about it. So again, the very first thing I'm going to do that I want to point out to you is I'm going to put some of the givens in. So let's put 12 volts here, and obviously this is our positive, this is our negative. We don't know, it looks like it wants us to solve for that total current, right? That's coming out of this and then going through the different branches. We do know that we've got R1 is labeled as 2 ohms, and we've got R2 at 4 ohms, and R3 at 2 ohms, and then R4 at 2 ohms. So one of the things I want to point out to you, to not let you get confused here, or hopefully to avoid confusion, is that in this area here, we know this is coming out, this is a resistor in series, and then we go into the parallel branches, right? And this is one branch that comes down, and then there's one branch that goes through this resistor, and then goes through this resistor. Don't let the diagram, though, confuse you. R3 and R4 are actually in series, right? So I always like to find these series circuits because those are the easiest to kind of define. And what we're going to do is we want to find out the total circuit equivalent resistance, because then we could solve for the total circuit current. So the very first thing you can do is we're going to rewrite this again. I'm going to just rewrite it down here below a little bit. Like so. I'll try to keep it fairly close to the diagram we have above. And then rather than having two resistors, I'm just going to combine those resistors, because we know resistors that are in series, right? Well, we don't need that part. These two resistors, right, R3 and R4, well, in their series, we just add them together. So I'm going to make this one resistor of 4 ohms. And then I'm going to add back in R2 right here, right? And then you got R1, and I'll just put in our information, and R2 was 4 ohms, and we got 4 ohms over here. So now, right, we need to find out the equivalent resistance of this leg. Let me make sure you understand. So over here, so the current is coming through this resistor, right, and it splits into these two areas. So we want to find out what the equivalent resistance is of these two, right? So in order to do that, I'm going to use our formula, which is what? That's the, sorry, let me get that. 1 over RT, right, is equal to 1 over 4 plus 1 over 4, which just should look familiar, right? This is the same equation I think we just did on the previous one, just in a different layout. So 1 over RT is going to be equal to what? 2 over 4, right? And then if we do the inverse of that, R2 would be equal to 4 over 2, or 2, right? So our total resistance of those two branches, right, is going to be 2. So watch what's going to happen. I'm going to rewrite this equation again, right? But you'll notice we just keep simplifying it. So I'm going to write it right here. Come over, and then here. And now R2, right, with that combined resistor right here, right, is now one branch coming down, which is 2 ohms. And then this comes up, and then we had that other resistor here, which was what? R1, which was 2 ohms. Which means that we would add those two together, right? And we'd end up with the resistance of this thing being a total of what? 2 plus 2, 4 ohms, right? And so we could literally rewrite this whole problem now as one big circuit here if we wanted. If I erase this stuff, right, we can combine these two, and we end up with what? 4 ohms, right? 2 plus 2. So based on that, now we know we have 12 volts here, so we can figure out our current, right? So 12 divided by 4, right, according to Ohm's law, would mean that we've got what? 3 amps coming back and 3 amps going out. So let's walk ourselves backwards here a little bit, back to our original diagram that was up here in the corner. I'm going to see if I can get this. Let's blow this up here a little bit. On there. Let's take a look. So on this guy, right, we know that we've got, sorry, I need to get this a bit more back to where we were. Sorry. We're going to have 3 amps. Whoops. 3 amps coming out of here. Or, yeah, 3 amps, right? 3 amps now. And we got 3 amps, right? So we know, for example, all right, well, what's the voltage drop across this guy, right? If we're going to put that voltage meter in here, we come down, what would be the voltage? Well, 3 times 2 would be what? 6. And that's, again, just using Ohm's law. So we got a 6-volt drop. Now we've got, coming out of here, out of the amperage here, we decided that on our previous diagram, right, that whatever these legs end up being, right, they've got to end up equaling the total amount of current going through here. So a certain amount of current is going to go this direction, and a certain amount of current is going to go that direction. Well, we know that both these legs are actually equal in resistance, right? So it's pretty easy to figure out that we would have 1.5 amps and 1.5 amps going out each leg, and then that's how much would be coming back. That's how much would be coming back, and 1.5 and 1.5 would add up to the original 3 amps. Now, if we wanted to figure that out, you most certainly could, because you know if you've got 12 volts here and you got a voltage drop, at this point we would have what, 6 volts. So 6 volts here divided by 4, right, would give us our amperage. So that would be 1.5, right, amps coming through here. And then if you wanted to know the actual voltage drop that's going on between here, well, you know you got 1.5 amps, right, times, what's it, 4 would give us our voltage. So R2's voltage would be, so R2 would end up being what, 4 times 1.5, which is 6 volts. And then if you do that for the other two legs over here, right, over here, you would multiply 6 times, or I'm sorry, 2 ohms times 1.5, which will give you 3. 2 ohms, again, a series, so you know it's 1.5. So the important lesson here to understand is that in a series circuit, right, all that voltage is dropped that comes out as it goes across. In a parallel circuit, right, both legs here in this case are going to drop that same amount of voltage. But you will notice that the current in a parallel circuit, it decreases, right, as we go through. So you have the voltage, but you don't have the current. In a series circuit, right, you can maintain that current throughout the complete circuit. So just kind of an interesting tidbit to pay attention to. All right, so let's look at the series parallel worksheet um, number, the worksheet 1, but the question number 3. Let's see, which is a little bit, looks a little bit more complex, but really it's not. I'm going to put it up here so we can just kind of get a look at what's going on here. Put it up in the corner there. So, I guess I should have made it a little bit bigger. We're looking for the total current value. So I'm going to go in here, just kind of pencil in, right, our positive and negative sides. I like this. It just kind of keeps my mind straight. So put 12 volts in there. And then R1 is 2 ohms. And R2 is 8 ohms. And then R3 is 2 ohms. And R4 is 4 ohms. And R5 is 2 ohms. So the very first thing you might notice, we don't know the current, right? So we're still trying to solve for that total current value, which means we're going to have to get somewheres where we can understand what the total resistance is of the circuit. So the very first thing I like to do, I'm going to focus, right, in this case, and I don't know if you've already seen it, but let's look at this branch right here. See how this branch comes out, and we got 3 resistors in series. So I always like to start with that type of area when I see them. Series are always easy. So what I'm going to do, I'm going to rewrite this this guy down here, and then we'll just kind of work through this. This is R1. Get that resistor going. I'm going to go over here and put this side in, and hopefully, you know, this is getting a little easier for you guys as you see it drawn out. We've still got our 12 volts here and our 2 ohms. It's not really necessary at this point in our 8 ohms. So what I'm really looking at again is, what do I do with this branch here? Well, I'm going to add those values together and kind of, I'm going to make it look like one resistor, right? So I'm going to go over here. Now I'm going to add 1 resistor in here, 1 resistance total. Then I know 2 plus 2 plus 4 it's going to give me 8 ohms, right? So again, I got another 8 ohms resistor. We like it when it's like this, kind of simplifies things. But again, let's just do the math on it. So again, if I want to solve for the equivalent, right, and let me make sure I'm pointing this out in case you missed it. So now I got current coming through here, and then it branches off. So I need to figure out what's the equivalent resistance between these 2 branches so I can rewrite this, right? So in order to do that, we use that RT value, right, is equal to 1 over 8 plus 1 over 8, which is going to give us an RT value of 2 over 8. And then we got to do the reciprocal of that, right, which is going to end up being 8 over 2 or 4, so 4 ohms, right, exactly half of that. So now we can actually redraw this sucker again, right, come down here, just like that, draw it in here, and now we've got one resistance from those two legs, right, and you see what we did, we just made it a parallel circuit. We got the 2 ohms, which was R1, and now the equivalent resistance here is 4 ohms, right? So now we know in here we got 12 volts. This thing actually becomes what? Well, the circuit really looks like this now, which is what's kind of cool about this when you start doing it. So you've got 6 ohms, and then this comes back here. Now look how simplified we've made that from 12 volts. But ultimately, what do we end up solving for? Well, we know that according to Ohm's law, we divide volts by resistance, our total resistance, we'll get the current. So the current in this thing going up, right, is going to end up being what? 2 amps. We got 2 amps coming out, 2 amps going back. So now we can go back, and we've already solved our question right there, right? Total circuit current is 2 amps. That's kind of easy. But what I like to do is just kind of say, hey, can I solve the rest of it? And I mean, you can. And so I don't want you to think this gets too difficult, but you got 2 amps coming out here, right? And 2 times 2 would give us a 4-volt drop here, right? 4 volts would be our drop on this if we were to check on this end and this end, right? Which is going to leave us 8 volts at this point, right? 8 volts. And then we could sit down and figure it out for each one, right? We know that we got 2 amps coming out, right, at this point out of that circuit, but how much is going this way and how much is going that way? Well, because we know the total resistance, right, based on what we saw down here, even though it looks complicated, it's 8 ohms on both sides. No matter how those resistances are figured out, it's just going to split that. So, I mean, you can do all the math in the world, but the bottom line is that's going to come out to what? Well, that's going to be, sorry, the wrong guy here. You're going to have coming out here 1 amp, and on this branch coming down, how much? Yeah, 1 amp. 1 amp actually right here. I'm sorry, all the way through, because this is a series circuit, right? So it's always the same. So if you add 1 and 1 together, coming back here at this point, right, you're going to end up with 2 amps, which is what we got, right? So not so tough at all. And hopefully you're seeing a pattern, and you can actually determine the voltage drop across each one of those resistors, because you know if 1 is here, well, 1 times 1 amp times 2 ohms will give us a voltage drop to 2 volts. And then this one, yeah, 1 times 4 is 4 volts, and 1 times 2 is 2 volts. You add those together, you get 8 volts, right? So yeah, in a parallel leg, right, we're going to actually end up getting less current going through the circuit when we go into the parallel side, but we're going to have the same voltage delivered, the same pressure in each line, okay? So, all right, well, hopefully that's working out, and hopefully you're getting a better image of this, all right? Thanks a lot. And again, guys, if you got any questions, you're always welcome to ask me.